irreversibility, particularly the role of deep ocean warming-induced SST pattern. So sea level rise is one of the critical issues in climate change, which mainly driven by the melting of land-based ice and ocean thermal expansion. While the melting of glaciers and ice sheets is the main driver of irreversibility of sea level rise, even if we only just considering ocean's thermal expansion, it shows irreversibility. Solomon and I have shown that thermal expansion continues to rise even after the CO2 emissions are set to zero. Previous studies have attributed this to the ocean's large thermal inertia, meaning that the ocean's large heat capacity leads to continuous ocean warming and expansion. However, there is some ambiguity in this explanation because ocean warming also triggers several indirect effects that amplify the warming itself. So, as Professor Wang introduced, for example, Ueda have shown that during the recovery period, oceanic content does not recover to its initial level, showing the irreversibility. This means that deep ocean still contains a lot of heat in spite of the decreased CO2. This retained heat is released at the surface with the particular SST pattern, specifically in the Bering Sea, the North Atlantic, the stratocumulus steppe region, and Southern Ocean. The higher SST regions correspond to the less stability regions, making it easier for heat to be released at the surface. This particular pattern could enhance ocean warming through the positive feedbacks. For example, through the low cloud SST feedback, this ocean warmed SST pattern could reduce low cloud cover, further allowing more solar radiation to reach the ocean surface. This would further enhance ocean warming and continue to additional sea level rise due to thermal expansion. Therefore, we hypothesize that SST patterns induced by deep ocean warming delay ocean cooling, thereby perpetuating thermal expansion and increasing the irreversibility of sea level rise. To support this, as Professor Cook mentioned, we used the CSM2 emission-driven experiments conducted by Yonsei University. The CO2 emission is increased according to the SSP 585 scenarios for 50 years and then decreased until the CO2 concentration reaches to 2011. After this point, CO2 emissions are maintained at zero. There are 400 years total duration. So here are the results. The black solid line represents the global mean sea level. Sea level continues to rise despite the negative and zero emissions. Sea level depicted here is solely due to the ocean's thermal expansion without melting, which is shown by the continuous increase in oceanic content. This is because, like other climate models, our model does not account for the land-based ice melting. So how does thermal expansion persist? We examine the cumulative net surface flux, which is shown in the sky blue line, which corresponding to the oceanic content. This means that ocean continues to absorb heat from the atmosphere even after CO2 concentrations return to present climate levels, driving the ongoing thermal expansion. To identify the factors contributing to the increase in cumulative net surface flux, we decompose it into long wave, short wave, and turbulent heat flux. While the long wave and turbulent heat flux changes closely follow the CO2 concentrations, short wave shows an increase and remains positively regardless of CO2 forcing. This suggests that the short wave is the main driver of the increase in cumulative net surface heat flux. To further understand this positively remaining short wave, we decompose it using APRP method. So let me briefly introduce this method. Short wave changes at the top of the atmosphere can be described in the insolation change and the albedo change. Insolation is fixed in the model, therefore all changes in shortwave is due to albedo change. APIP method allows us to decompose insolation, solar radiation by theoretically fitting albedo components by using a simplified shortwave radiation model. So we can decompose shortwave into shortwave cloud, shortwave albedo, and shortwave non-cloud. As you can see here, the increased and positively remained shortwave is largely attributed to the consistent positive contributions from shortwave cloud. This leads us to the next question: how has the cloud changed? Low cloud reduction is the main reason for the increase in shortwave cloud. So we can summarize content so far like this. Continued sea level rise is due to the continuous absorption heat from the atmosphere, which is attributing to the positive shortwave and low cloud reduction. So let's close look at the local pattern of these changes. So these are the shortwave changes patterns during the ramp up, ramp down, and last 150 years mean. All patterns are subtracted from the present day control run. The increased shortwave regions correspond to the reduction in low cloud cover, and further to the SST warming regions. Warming regions. These SST patterns during the last mean period corresponds with the devotion warming-induced warming described at OFL. So changes in shortwave and low cloud depend on how SST pattern is formed. So in other words, SST pattern is important for the positive shortwave. To validate this, we performed the EMIB experiment. So at first, we tried to reproduce CSM2 results using this SST fixed EMIB experiment during the last mean period. So EMIB will reproduce CSM2 results in the pattern of shortwave, low cloud, and TS, and also the zonal mean amounts. So we further decompose these EMIB total results into the pattern effect without mean warming, and mean warming effect without pattern, and sea ice change effect. Below are the shortwave pattern changes contributing to the prescribed SST pattern. So observed shortwave patterns in the equatorial and middle latitude primarily driven by the pattern effect. This suggests that if there is no specific SST pattern, there will be no positive shortwave. To facilitate a quantitative comparison, we have also included a bar graph. The positive shortwave observed, this is the global mean shortwave value for each experiment in the last mean period. So observed positive shortwave in both in the CSF2 and EMIB is primarily attributed to the pattern effect. If there is only the mean warming effect, there the shortwave would be negative, suggesting that there will be no sustained ocean warming and further contributing to further sea level rise. When we decompose shortwave into cloud, non-cloud, and albedo, this pattern effect is mostly comes from the shortwave cloud pattern effect. So here is the summary. Devotion warming induces specific SST pattern that leads to enhanced warming in certain regions. This warming reduces low cloud cover, leads to the increase in shortwave radiation. As a result, the less ocean heat is released, further contributing to the sea level rise, irreversibility due to ocean star expansion. This is all I have prepared. Thank you.